If you look at nature, there are some stunning colour effects. Rainbows are amazing things. Stunningly bright, vivid butterflies from South America. Dragonflies, how do they achieve those gorgeous greens? We just need to know. If you take a butterfly and you look at its wing scales, it's got very tiny wing scales, about 50 microns by 100. We found that within the wing scale, which is more or less fingernail material, the butterfly had created tiny sculpted structures, nanostructures, which gave interference, which gave diffraction. Those effects combined can give you a variety of different vivid colour effects. From the electron microscope images, we discovered an intricate structure in the wing scale of the morpho butterfly. And what we decided to do was to replicate that on a much larger scale. Here we have a structure corresponding to the scale of the wavelength of microwaves, with details, ridges, and with these Christmas tree structures internally. Then when we shine microwaves at this, it responds like light does to the butterfly wing scale. By unravelling the butterflies, we discovered a whole raft of new metamaterial type structures. If you structure matter on a fine enough scale, it doesn't respond in the simple way like a bucket of water or a piece of aluminium. It has new properties, new optical properties, new properties for different wavelengths. There was a fascinating paper by some South African scientists who were looking at a particular moth. It's got a metallic gold spot on its wing, and it turns out that it uses a zigzag grating, which is just basically a grating, and you zigzag it. Zigzag gratings haven't really been studied before, and they're fascinating. They have weird polarization properties, odd diffraction properties. We then make zigzag gratings, we then metallize them, and they have very interesting optical diffractive properties. If flat silver is placed into the scatterometer, all we would see is reflected green light. If we pattern the silver surface with a grating, then what we see on the screen is some missing portions of light. The light has gone into exciting surface plasmons. Scaling up from the visible to microwaves, we make samples of this kind. These scatter microwaves as the butterfly wings scatter light, but if we now metallize these, they will have very different properties which you would not achieve in a butterfly wing scale. They will reflect microwaves in particular directions. They will stop certain frequencies of microwaves. You can even make lighthouses, if you like, of microwaves, so you can steer them around. This is useful in a variety of applications, one of which is in RFID tagging. RFID tags are going to be placed on many objects to keep records of where they are, stock checking, movement of goods, drugs, blood samples, etc. Conventional RFID tagging, the success rate of monitoring a large number of RFID tags can be as low as 70–75%. By using these structured metal surfaces, we've raised that success rate to well above 99.9%, which is really a massive improvement. Our most recent work is to combine the patterned metal surfaces and the surface waves they have with some of these new ideas in what are called transformation optics, theoretical developments in recent years, where you take an ordinary optical design and you use a new mathematical approach to design new types of structures. And one of the things we're playing with most recently is an object called a Lundberg lens on a surface, which if you shine a surface wave, which is a plane wave at the lens, it focuses it to the point on the circumference of the lens. I go around from place to place talking about physics, and I find that from 3-year-olds to 93-year-olds, they're still fascinated. How does it all work? That's it, isn't it? How does it all work?
So the theory for a perfect lens actually originates in about the 1960s. A guy called Victor Veselago, he said that you could get something called a negative refractive index, which essentially means that when you look at a prism or something like that, light tends to bend a certain way. And he proposed that you could get light to bend the other way if you so wanted. And this is the basis behind a perfect lens. Current limitations with optical microscopy are mainly due to something called the diffraction limit, which was devised by a guy called Ernst Abbe in 1873. Now the problem with that is that light is a wave, and as a wave it diffracts in certain ways. And the diffraction limit means that you can only resolve down to a very small spot, but a fixed size of spot. So you can get to about 200 nanometers across, and that's about, well, we're talking millionths of a millimeter here. And you can't go any further than that due to the wave-like nature of light. So that's a big problem.
The refractive index of a material is how much light slows down when it travels through such a material. So the light is travelling from air and into water. And when it hits the surface, it reflects a little bit, but it also transmits, and it bends at an angle that's related to the difference in refractive index between the two materials. Now, water and pretty much all materials in nature have what's called a positive refractive index. So what's happening here is the light is going from air into water, and you can see that the light is bending towards the normal when it enters the more dense material, which is the T. If this wasn't T, but a negative refractive index material, something different would happen. The light wouldn't be on the left-hand side of the normal, it would instead be on the right. So light would come in this way, but then bend back on the opposite side to the surface normal.
The actual idea for a perfect lens, for it to be used to image things, came up with a guy called Sir John Pendry in about late 1990s, and it was demonstrated in early 2000s. And this idea basically uses a metamaterial, so a material that's comprised of very small structures, much smaller than a wavelength of light. And by arranging those structures in certain ways, you can amplify light waves and get them to diffract the wrong way. And you can see images you wouldn't normally be able to see on a much smaller scale.
With nanotechnology, you're dealing with things that you can't see. So it's really important that you have these tools that allow you to see a nanoparticle inside a cell that's really complex. So if you're doing bulk measurements, just on a lab bench, it's difficult to interpret the results, and that's where microscopy and good optical or high resolution optical microscopy and electron microscopy are so important, and more so now that we're dealing more with nanotechnology.
So we look at the interface between nanotechnology and immune cells using nanomaterials to try and control the responses where the body decides, the immune system decides whether it's going to attack an infection or a cancer or whether it's not going to. And the reason that's a nanotechnology or a nanoscale problem is because what these high-resolution microscopies are beginning to reveal is that there are a lot of exceedingly small structures, so down to the level of tens of nanometers or less. And these structures are critical to the way cells talk to each other. So when your immune system decides whether it's going to attack something, there are spatial structures at that size which are helping to mediate that decision. So the combination of, so the ability to image those is vital to understanding that, and it's also vital to understanding how to control that process if you want to for therapeutic reasons.
In our group, we're interested in looking at the interaction between a cell and nanoparticles. And you can't currently see that in the conventional optical microscope. But if you could watch where an individual nanoparticle is interacting with the cell, what compartments it's going into, what effect it has on the cell structure, that would be really interesting to do in a live cell.
And cells, when they're alive, they're generally quite transparent and colourless. So you'll have to stain them if you want to see them, and that is actually obviously influencing the cell itself. And you don't want to do that because then it starts messing with the processes.
Not only are the imaging techniques coming online, but also nanotechnology techniques that enable us to build structures on the same size as these vital structures mean that we can interact directly with these little features. We can control their size, try to control their size, or to pull them around, or to position them. And so these two technologies coming in parallel should really show some exciting results.
Perfect lensing principles have actually been demonstrated already on things like up to maybe 20, 30 nanometers, which is already a good, something like 10 times below the diffraction limit. So we've shown that it works. It's just going to take a bit more time and maybe a little bit of someone's clever idea to make it actually a reality.
At our Textiles Nanotechnology Laboratory, we work on understanding fundamental chemical and physical phenomena that happens at dimensions below 100 nanometers. And it happens that this phenomena is highly relevant to polymer and fiber science. And what we want to do is to specifically aim this knowledge to modify existing materials, to create new fibers, and to develop new measuring techniques for this phenomena. And we are very fortunate that we are located in the Department of Fiber Science and Apparel Design, so we closely interact with students and colleagues that work on apparel design. There are many advantages of using nanotechnology in textiles because we can impart functionalities to textiles in a more controlled manner and with less raw materials. We can also create new functionalities. In our lab, we like to manipulate fibers into doing things they don't like to do. For example, we can make cotton to kill bacteria. We can make cotton to conduct electricity. We can make cotton to serve as an electrochemical transistor, or cotton to capture toxic gases or active compounds such as vitamins or cosmetics. So many advantages to use this knowledge at the nanoscale and apply it into larger surfaces like textiles. I believe that the interactions between scientists and designers are extremely important because these interactions can create spaces of incredible intellectual and creative wealth. Scientists and designers follow two different ways of thinking, two philosophies. And if we combine those two philosophies, we can make our science more relevant and appealing to the community. Scientists used to tackle a big problem, by dividing the big problem into smaller problems. We find local solutions, and then we compile these local solutions into a bigger solution. But designers have a more holistic approach. They see the final concept from a larger perspective, and they can actually come back down to the details. By taking advantage of these two approaches, and interacting together, we can provide solutions to problems that are not possible by either a scientist or a designer working by themselves. And I can say that I'm a better scientist, and my science is better because I've worked and interacted with designers. Well, that's a difficult question because I want to think that most of my projects are very exciting. But my favorite molecule is cellulose, and specifically cotton. And we have worked on making cotton antibacterial against E. coli and Staphylococcus bacteria. We have also created color without using dyes or pigments, just using nanoparticles. We had made cotton electrically conductive, and also use cotton as a substrate to create electrochemical transistors. And we created cotton into a structure capable of capturing gases in a very selective manner and encapsulated compounds like medicines or vitamins or cosmetics. On the basic level, we also have discovered very unique phenomena and developed new techniques to measure existing phenomena that can produce better lubricants, better anti-static treatments, and better coatings for textiles. All these projects involve a large number of students over many years, students with different backgrounds, international collaborators, and funding agencies that have made all of them possible. So I think these creations can see the high street. We produce mostly chemistry that is water-based and that can be replicated using existing textile manufacturing facilities. We are a university, and our main goal is to produce science and train the next generation of scientists. But by working with companies and industries that have licensed these technologies or hired our students, they have been able to incorporate these new developments into their production lines. There are many challenges for the interaction between scientists and designers because we are training totally different approaches and philosophies, so we have developed different sets of values or what is important to each one. For example, for a scientist, getting a publication in a high-impact journal and getting a lot of citations from your colleagues can be a very worthy goal. But for a designer, having a very well-critiqued and publicized collection or exhibit can be equally important. The trick is to respect each other's disciplines, and I believe that we can achieve better outcomes by interacting together. And take a look that I don't say working, I say interacting, because that's the key. If these two disciplines interact at each step, instead of simply dividing the task, we can achieve a better outcome. If you use the approach, I do this and you do this approach is only additive. You are adding expertise and skills. But by interacting with each other, we can create a multiplier effect, a much more powerful outcome. Perhaps the issues of scales and dimensions is a difficult challenge because we see small things and they see bigger things. We see the world with different magnifying lenses. But it's a great and fun experience, sometimes frustrating, sometimes challenging. I will say that other challenges can be people in your own discipline or in your own community that have a very traditionalist or Puritan view of your field. So I will tell you, when I started working in these endeavors of collaboration, I was given a warning by people in the science side that I was wasting my time working with designers. And I was reminded by the designers that I was not one of them. But the key is to smile and to move on and use that, believe that these multiplying talents can be a worthy goal. As I mentioned before, I'm a better scientist because of these experiences with designers. I still produce my scientific papers, my patents, my developments coming from my lab in a scientific traditional environment, but now I can make science more relevant to the community. And I can argue that it's equally complex to design a molecule than to design a dress. We just need different type of skills and interests, and we can work together. This can make happen and can produce an outcome that is not possible but each one working by themselves. So the future is exciting and unpredictable because now, because of nanotechnology, now we have unique control of matter at the nanoscale. So we can create unique functionalities in clothing that were not possible before. We can make clothing to be an interactive surface that can serve, for example, as an electronic sensor without using wires. We can create textiles that can give you medicine when you sleep in your pajamas, textiles that will never get dirty, that can change the shape or the color as a response to an external or internal stimuli. I personally see a lot of potential in creating this type of fashion that responds. Many areas or industries can benefit of these developments because we are using fibers, and fibers are the raw materials that are present in many products, from a toothbrush to pillows to air filters to shoes to carpets to even airplane structures are made of fibers. So I think these developments can be transferred to these industries and create new changes in new functionalities in different fields like preventative health, disease control, homeland security, medical and biological applications, and all of them can be great beneficiaries of these unique developments. I would like to see the garments not as an external object. I would like to see garments as being like a second skin, a skin that will react to your body, but also will react to the external stimuli. So if I'm in an environment that I need to be red, I can be color red. If I'm feeling sick, this same garment can provide me with the medicine. If I'm feeling cold, the same garment will provide me with heat. So these type of interactions to see the garment as a second skin is what we aim in our lab to produce.
In this paper, we analyze the development and the applications of nanotechnology in the field of anti-cancer treatment. Nanotechnology has been widely applied in almost all the fields across the whole economy, and including this anti-cancer treatment field. And especially, we notice that nanotechnology is going to play a more and more important role in the field of anti-cancer treatment. As we know, the mortality rate of most cancers is rather high. When other traditional treatment fails, doctors are looking for new solutions from the emerging technologies. So nanotechnology opens the new door in offering a more effective treatment. Nanotechnology is called also key enabling technology, which means that it can be applied in almost all the industries. A nanometer is very tiny, it's 1 billionth of a meter, and it's about 100,000th of the width of a hair. In our study, we use publication and citation data collected from scopers covering 13 years, including 7 cancer fields and 16 types of nanotechnologies. In some field of cancer treatment, if the mortality rate is higher than others, we notice that there is a very high nanocytation intensity in this field. However, if the mortality rate is relatively lower in some certain cancer field, and then the nanocytation intensity is also lower. So which means that in those most dangerous cancer fields, doctors are really looking new solutions from nanotechnology. We noticed there were two main technological trajectory waves. The first one was in 2000s, and including only one type of anti-cancer therapy. And then the second wave happened after 2006, even including more types of anti-cancer therapies. Which means that in recent years, doctors have noticed that the power of nanotechnology.
Okay, good morning. I'm very happy to be here. I'm glad to share some of our experience in developing sensors for biomedical applications. NASA Ames Research Center is one of the 9 NASA centers in the US, and we are located in Silicon Valley, okay, very close to Google and Intel, and about 10 minutes from Stanford. So there I run a nanotechnology group, and we have a lot of activities going on. I'm going to focus just the biosensor activities for biomedical applications. I also have strong collaboration with Pohang University of Science and Technology, POSTECH in Korea. I have some parallel activities there. I have graduate students and in developing a biofield effect transistor. So it's somewhat of a competitive technology to what I'm doing at NASA. There are 2 competing technologies. I really don't have any preference, one over the other. You treat them like you treat your children. You don't give any preference. But the market may decide completely, differently. That's a different story. And so I'm going to give an overview of all of those activities. Okay. So first of all, what is the criteria for a very well-designed biosensing system in the marketplace? First of all, small size and mass, and low power consumption, especially if it is going to be a portable unit, and if you want to integrate it with a smartphone, then it has got to be low power consumption. Again, minimal resources, minimal chemical resources, and minimal human processing, because if it has got to go to commercial level at the user level, and if the public has to use it, then you cannot design a system which requires a PhD for operation. So fairly well automated, reasonably rapid analysis, so that it doesn't take too long, negligible false alarms, and if possible, multiplexing capability to do multiple things. But you got to be very careful, because as scientists and engineers, we think we can design a chip which will do 9 things. Okay, that's a wonderful goal, but I'm not so sure whether it is a good idea for us to try so hard, because we are not the ones ultimately decide everything beyond us. Okay, it's not just the marketplace, it's the business development. What it is right now, actually, there is healthcare, at least in the US, is so expensive. Okay, everything is done by people wearing lab coats, and so their salaries are high, the insurance costs are high, so on and so forth. So if you're going to bring something, which is going to do at least one thing right, automated, that alone is going to save costs, okay? But all of a sudden, if you actually do something which is going to make 9 things, okay, the companies may not want to actually push it out in the market because there is not money to be made. Remember, the companies are there to make money. They are not there actually as a charitable organization. So there are a lot of factors beyond you and me, okay? So that's why multiplexing is very hard. If you can't make it work, don't feel bad. That's all I'm trying to say, okay? And multiplexing, and then reliability is very important, and ultimately a technology that is going to allow you to mass produce these devices so you can keep the cost fairly low, okay? So those are essentially the goals, okay? So the first type of sensor that I'm going to talk about is a nanoelectrode array, for biosensors. So these nanoelectrode arrays are using electrochemical techniques, okay, whether it is impedance spectroscopy or cyclovoltammetry or amperometry, whatever. And so people have been using carbon-based electrodes, for about 100 years. So why would you want to have another electrode, especially a nanoelectrode? Okay. What it is the electrical engineers, will tell you that, the noise is proportional to the surface area. So you take a traditional microelectrode or macroelectrode, and you have very tiny biomolecules that you want to detect. And so you have a large area, and you have a large noise, and you have a very tiny signal. On the other hand, you take the same microelectrode and you divide that into so many different nanoelectrodes. Now the size difference between your molecule and the electrode goes down, and you significantly enhance the signal to noise ratio. And again, there are multiplexing opportunities. So what is it that you can use for materials here? If you think of using single wall carbon nanotubes, looking at pictures of SEM, you always notice that single wall carbon nanotubes, they look like spaghetti on a plate, okay? So it's very hard actually to have controlled electrochemistry on single wall carbon nanotubes, controlling the size and also putting the functionalities and other kind of things. Even the multi-wall nanotubes grow like towers, and if they happen to be fairly big towers, all the nanotubes are right next to each other. On the other hand, carbon nanofibers are silicon nanowires or zinc oxide nanowires, and if you can grow them nice and vertical, okay, and what it is you have one electrode here, and then you have an identical electrode, nanoelectrode, exactly at a distance apart, the distance that you choose. What it is you can do a simple back of the envelope calculation. For a 50 nanometer electrode, the radial diffusion layer in electrochemistry requires that the neighboring electrode should be at least about 1.5 micron apart. So that way these two will act like individual electrodes. If they're any closer together, the diffusion layer of this electrode will overlap with the diffusion layer of the next electrode. Then if they all overlap, then it will begin to deviate from an ideal nanoelectrode, and all the diffusion layers, when they merge, then they will behave like a microelectrode. Okay? So that is the biggest issue. So the vertical carbon nanofibers, the vertical silicon nanowires, the vertical zinc oxide nanowires, whatever is your material of choice, okay? I'm not going to argue with you about one versus the other, okay? It all depends on your level of confidence and qualifications, how far you have advanced, okay? We have worked with carbon nanofibers long enough that we feel very comfortable working with them, okay? So that's why generally I don't enter into academic arguments about one material versus the other, because there could be compromises. So the way we do this is fairly simple. We start out with the silicon wafer. We used to do 4-inch wafer, now we do 6-inch wafer, and then we deposit a metal film, titanium, tungsten, tantalum, typically like in microelectronics, and then we put the catalyst deposition for carbon nanotube growth or nanofiber. So here we use nickel, we pattern the catalyst, and then we use plasma CVD, and then we grow vertical carbon nanofibers. Okay? And these carbon nanofibers are about 50 nanometers, and they are about 1.5 micron apart. And then we fill the gap between these nanofibers with silicon dioxide using TR-CVD. Okay, so that serves two purposes. One is that you can get electrical isolation between the neighboring electrodes. That's one thing. The second thing also, during operation, it has got a mechanical robustness, so the nanotube actually doesn't fall down like a grass on a rainy day. Okay, and so those are the two advantages. And then we do chemical mechanical polishing that exposes a tiny bit of carbon nanofiber. Okay, it's like the small whiskers on a teenager's face. Okay, the hair growth. So that's what it looks like. So if you take a look at a top view of the SEM image, so these white dots that you see are the carbon nanofibers poking out, maybe a couple of nanometers. And then it is actually on a sea of silicon dioxide. So this is the one that we package, and so you can bring your probes and you can attach these probes. The probes could be, again, depending on the target and depending on what is it that you want to use for a probe. It could be a DNA probe, it could be a protein, it could be antibody, it could be aptamer, anything that you want. And so this is a carbon chemistry, so you have to have your own protocol to attach the probe. Okay? And then you bring your target. When they hybridize, essentially you can do cyclovoltammetry or you do electrochemical impedance spectroscopy. Okay, so this is a nano electrode. So I'm going to give you a couple of quick examples. Troponin is one of the biomarkers for heart disease. We have done all three, troponin, myoglobin, and cardiac reactive protein. And we have done both the cyclovoltammetry and also impedance spectroscopy. And I'll use the impedance spectroscopy to explain. So the bare electrode is the blue color, and then after you attach the antibody for troponin, that is the purple color, and then you get the impedance basically concentration dependent impedance for when you bring the troponin target. And so these are various concentrations, and the lowest concentration that you see 0.25 nanogram per ml itself is well below what the medical community is looking for. And so this is done with the laboratory. This thing we have since then done in a human serum, and that hasn't been published, so I don't have the data yet. With the human serum, actually the concentration levels are a bit higher, but not terribly bad, but still under the limits the medical community is looking for. And the next one is cardiac reactive protein. Again, similar curves. The bare electrode, and then after the antibody attachment, and then concentration dependent impedance spectroscopy curves. Recently, just end of February, a visiting scientist that I had from India, he finished a multiplexing operation. We have a 3x3 array. I think I have an electrode here. Yeah, so essentially this is what it looks like, a 3x3 electrodes, and with the contact pads looking like this. So he used the first three for myoglobin, and the middle three for the cardiac reactive protein, and the bottom three for troponin. So we are just in the process of analyzing the results. So this is actually the old processing that Bugraph 4-inch wafer, but now we migrated to a 6-inch wafer, so we get quite a bit of chips from each effort. And in fact, one without patterning is the one that I brought a couple of days ago and gave it to Ravivan, and I'm hoping that she could do her cancer diagnostics work using one of these chips. Hopefully we should be able to give her these pattern chips also in the future. So as you can see, this is one approach for lab-on-a-chip applications. Early cancer detection is a potential, so that is one of the things that I'm hoping to do with Ravivan's help here. Environmental monitoring, it is something that we are working on currently. Pathogen detection, we have already done things like, oh, I'm sorry, I forgot. Okay. For ricin detection, we have already done the work. And we are also beginning to look at food quality monitoring, because food quality monitoring in many cases, you can convert the problem into water quality monitoring, because many of the contamination, if you take a cabbage, things don't go all the way into the to the center, and this is what I was told. Okay, so as an engineer, I don't have any knowledge about some of these things. I just learned from other people. So this is more or less like a surface contamination. So what it is these food companies, the food processing centers, they essentially do a quick wash using pure water, and then they collect that wash water, and then they do analysis using instruments. So now you take that water and then you do use one of these biosensor chips, okay, whether it is E. coli or salmonella or some other bacteria, protozoa or whatever that you are looking at. So the point I'm trying to make is you can do food quality monitoring essentially by converting the problem into a water quality monitoring type problem. Okay, so you can see there are a variety of applications for this type of biosensor. So moving along, that I want to talk about the comparative technology from my Korean group. Okay, and so this is something that I've done in the last 3 or 4 years. So in the NASA approach, there are two things. One is that we were using an electrode. It's electrochemical. The second thing is we were using a material, exotic material like a carbon nanfiber. Whereas on the other hand, so this is just your simple FET, okay, field effect transistor, similar to what we have on our computer chips. Okay, the only difference is in the computer chip, the FET we have, the transistor we have, is dry. Okay, whereas if you're going to do bioanalysis of any kind, you will be dealing with water or urine or blood. Okay, so this is going to be a wet FET. Okay, so in that sense, you have a source and you have a drain, but you replace your standard dry gate with the reservoir area with where you can put your electrolyte or liquid or whatever sample it is, and then you also fabricate a reference electrode. Most people have a reference electrode which is pretty much separate, but in POSEC we have exceptional nanofabrication capabilities. So when we fabricate an 8-inch wafer, we also fabricate a reference electrode right on the chip, so it does not have to be external. So we do all of these things, and the advantages are you don't need to do any kind of labeling, and there is no expensive micro readers. So the way the BioFET works is you have when you operate it without any of the electrolyte or any of the antibody or anything, you have your standard current voltage characteristics for a given gate voltage. But now when you attach an antibody and you measure the current voltage characteristics, it will shift a little bit. Okay? The electrical engineers will call it threshold voltage shift. And then when the target and the probe, when they hybridize, there will be a further shift. So this shift will be unique. Okay? It is still important that you do all the surface protocol correctly, so there is no non-specific binding. Okay? So just because you have a wonderful electrode or just because you have a wonderful BioFET, that doesn't mean selectivity is automatically guaranteed, because if you have a target or if you have a probe which sticks everywhere and then you have a lousy surface in the neighboring area, you are going to have binding from all over, and they may contribute to the current, and that may confuse the signal. Okay? So no matter what you use for your diagnostics, it is your responsibility to make sure that the surrounding surfaces are such that you don't get into the problem of non-specific binding. So that's always an issue. You got to work with them. Okay. So this is a device fabrication. I don't have time to go through all of that, but I just want to point out that right over the gate area there is a small reservoir where you put your sample. Okay. Otherwise it's a standard source, drain, everything. What we have here unique is the silicon nano wire. Okay, so that's what we use for the material. It's not a silicon thin film like you have in your computer chips, but it is a silicon nanowire. But this silicon nanowire is not a bottom-up nanowire. It's not grown using catalysts, because as wonderful and as sexy as it sounds, and you can get a Nature paper, I honestly do not think it will anytime be viable or technically it's going to be commercialized in God knows how long, okay? Because it's very difficult to do it on large-scale wafer, and yeah, it's just a waste of time at this point, okay? On the other hand, I don't have the patience. I'm an engineer. I generally don't pay that much attention to Nature and Science papers, and so I like to see something in my hand which I can hold as quickly as possible. So what it is the top-down processing is much easier because it's very well known. The only difference between the standard top-down processing at Intel and the one that we do at Postec is that one in Intel is thin film. Here we make them into nanowires, and I'll show you how the nanowires look like. Okay, so this is what the nanowires look like. We have actually a couple of different approaches to do. So on the channel area, so that is the width going in that direction, we use 10 or 20 nanowires. Each nanowire is like 10 nanometer diameter. Okay. One thing that you got to keep in mind is when you are doing a biosensor and you are talking about a transistor, remember you are not constrained by Moore's law. Moore's law is for the computer chips, okay? Make it smaller and smaller and smaller. But here, our goal is different. We still got to be able to put 1 drop of blood, or 1 drop of urine, or 1 drop of water, okay? 1 drop, takes a lot of area and volume, okay? So we don't need to make the source and the drain right next to each other like Intel is trying to do today, okay? They could be fairly far apart. Okay, they could be like 1 micron apart or even a couple of micron apart. But one thing that you got to keep in mind is if you have 2 microns apart and you have a 10 nanometer wire, it might look, behave like a bamboo pole, and it could just flex, or it could even break. Okay, so the students I had at Postec, they came up with a very clever idea. Instead of having these kind of straight line nanowire, they also have a honeycomb like nanowire. So essentially, it looks like a honeycomb, but it's not a big deal. When you do lithography, you use a CAD drawing, and instead of doing straight line nanowires, they do honeycomb on the CAD drawing, and then you do the etching. They can make honeycomb type nanowire. So this is basically not only mechanically more stable, but it also supports the supporting surface area is much higher, so it can hold more volume of your probe and the target and so on and so forth. So that's what the device structure looks like. I think I'll skip all of these things. So the first one is carcino embryonic antigen. So the 3 curves that I was talking about, the one on the rightmost is your standard IV curve, and then after you put the antibody, and then after you have the target. So the expanded version shows these curves nice and separate. The sensing limit for CEA that we got using the FET is 5 attomolar. Okay? I think the sensitivity of the BioFET would be higher than the carbon nanofiber electrode. Based on we haven't done a one-to-one comparison yet, but my gut feeling is that this will work much more sensitive. It's also since it is a silicon base and you can do it on 8-inch wafer, I have a feeling this will be probably closer to the market in Korea faster than the one that I could do in Silicon Valley. Okay, so that's what I think. And we have also done AFP, and I don't have time to go through all of these things. And a couple of things that I want to talk about. I won't have time to talk about things in detail. So far, the biomedical application that I talked about is, I keep forgetting to use the microphone, but I think my voice is loud enough, it carries all the way to the end. It's a small room. So that's based on liquid analysis. Okay? On the other hand, the medical community in recent years has been coming up with increasingly, more and more biomarkers in human breath. Okay? Again, as an engineer a few years ago, when somebody told me that a human breath has got about, I don't know, something like 200, 300 organic compounds, I was astonished. And apparently what it is some of these organic, I mean, the constituents of our breath, they can act like biomarkers. For example, acetone in diabetes patients, they generally have excess amount of acetone in their breath compared to normal population. And people who are going through kidney dialysis, they end up having excess amount of ammonia in their breath compared to normal population. So if you can do gas and vapor analysis, again, like what's going on here at Nanotech, because at Nanotech there are two groups doing gas and vapor analysis. One is focusing on environmental monitoring like nitric oxide and other kind of dirty things in the air. The other group is focusing on food safety, like looking at things coming out of mangoes or whatever. But potentially you can also do biomedical using the same setup that they have. They just got to do the training of the sensors, okay, for acetone or for ammonia. So it's still doable. So we make a gas and vapor sensor. So it's a very simple one. It's a silicon-based approach. Unlike the tin oxide nanowires being used at Nanotech, we use carbon nanotubes, and so it enables room temperature operation, so you don't have to heat it. Nevertheless, we build a heater in there just to clean up. Every time when you have to clean up the sensor, you can use heating. So this is like a bus bar electrode and interdigitated fingers, and we purify the single wall carbon nanotubes, and then we do inkjet printing or drop casting. So the way you do, when you do biosensor, the selectivity is guaranteed by choosing the probe, okay? But on the other hand, when you do gas and vapor analysis, it's electronic nose. The selectivity is not guaranteed by a probe or anything. What it is it functions like, okay. How much time did I get? 20, 30 minutes? 25, okay, so I'll finish in a couple of minutes, okay. So the selectivity is guaranteed by doing pattern recognition. So the way we do that is, I think I'll skip that. So we fabricate 1 centimeter by 1 centimeter chip with 32 sensors, 8 here, 8 here, 8 here, and 8 here. And but not all 32 of them are identical. Some of them have single wall carbon nanotubes, pristine. Some of them have nanotubes with the palladium. Some of them have nanotubes with the gold particles. So they're all different. So what it is when you train them, the 32 sensors in the lab, they give 32 different responses, and you save that in your signal processing chip. And you repeat this for various concentrations, various humidity levels, and various temperatures, and then you later on you use it for use a pattern recognition algorithm. So that's the electronic nose approach, which is what is going on here at Nanotech. Okay, except this is a much smaller chip with much more number of sensor elements. So it also, because of the carbon nanotubes, it is room temperature sensitivity, and it can give better sensitivity. So this is something that I'm hoping to ship to Nanotech. So the two groups here, one on the food quality and one on the environmental monitoring, they both can use these chips. So there were other things that by the way, I just wanted to mention that we have already put this the ChemSensor chip on an iPhone. We delivered 30 prototype phones to Department of Homeland Security. And also, this ChemSensor chip that I talked about, it is the one and only nanotechnology product that has been flown to outer space, okay? Because that ChemSensor has been monitoring air quality in the International Space Station, where the crew is hanging around the small place, and it monitors the air quality, particularly for formaldehyde, because formaldehyde is something that comes from the tiles and the carpets and other things. And time average over 1 day is 1 ppm. Okay, there are no commercial sensors which can pick out formaldehyde 1 ppm. If formaldehyde accumulates, it gives you headache and nausea and all of that. Okay, so that's something. And So I'll skip all of these things. I'll leave the summary for you to read, and I'll be happy to answer a few questions.
Thank you, Professor Mayappan. So we have time for a couple of questions, please.
Purified sample or real sample? That's real. So I mean blood sample, whole blood.
We have done both. We have done human samples too. Yeah. But as in every case, when you do the human samples, your sensitivity would be somewhat worse. Your goal is to try to get as close as possible, but generally, that's very difficult. Okay, but the important thing is, even with the human sample, if you can get sensitivity, a detection limit lower than what the medical community is looking for, then you have done it. Okay, yeah. Because sometimes we always again look for things, unrealistic goal. For example, in troponin, I don't see any reason why someone has to look for femtogram per ml or even picogram per ml, where a nanogram per ml is what the medical community is looking for.
You only mentioned sensitivity, but specificity, whatever, because there can be many cross reactivity. Okay, when you use whole blood in your parallel, multi-analyze sensors, cross reactivity between sensor and sensors. If you use whole blood, specificity is more problem.
What do you mean by a sensor to sensor?
Specificity.
No, I know, but what it is you said sensor.
Your nanowire sense, multi-analyze nanowire sensors.
Multi-analysis meaning when you have 3x3.
Yeah, right.
Yeah, the 3x3, the multi-analysis one, we just finished the work about a month ago. I haven't even seen the results yet. Yeah.
More questions? All right then. Let's thank our speaker, Professor Mayappan, again.
By some South African scientists who were looking at a particular moth. It's got a metallic gold spot on its wing, and it turns out that it uses a zigzag grating, which is just basically a grating, and you zigzag it. Zigzag gratings haven't really been studied before, and they're fascinating. They have weird polarization properties, odd diffraction properties. We then make zigzag gratings, we then metallize them, and they have very interesting optical diffractive properties. If flat silver is placed into the scatterometer, all we would see is reflected green light. If we pattern the silver surface with a grating, then what we see on the screen is some missing portions of light. The light has gone into exciting surface plasmons. Scaling up from the visible to microwaves, we make samples of this kind. These scatter microwaves as the butterfly wings scatter light, but if we now metallize these, they will have very different properties which you would not achieve in a butterfly wing scale. They will reflect microwaves in particular directions. They will stop certain frequencies of microwaves. You can even make lighthouses, if you like, of microwaves, so you can steer them around. This is useful in a variety of applications, one of which is in RFID tagging. RFID tags are going to be placed on many objects to keep records of where they are, stock checking, movement of goods, drugs, blood samples, etc. Conventional RFID tagging, the success rate of monitoring a large number of RFID tags can be as low as 70–75%. By using these structured metal surfaces, we've raised that success rate to well above 99.9%, which is really a massive improvement. Our most recent work is to combine the patterned metal surfaces and the surface waves they have with some of these new ideas in what are called transformation optics, theoretical developments in recent years, where you take an ordinary optical design and you use a new mathematical approach to design new types of structures. And one of the things we're playing with most recently is an object called a Lundberg lens on a surface, which if you shine a surface wave, which is a plane wave at the lens, it focuses it to the point on the circumference of the lens. I go around from place to place talking about physics, and I find that From 3-year-olds to 93-year-olds, they're still fascinated. How does it all work? That's it, isn't it? How does it all work?
So the theory for a perfect lens actually originated in about the 1960s. A guy called Victor Veselago, he said that you could get something called a negative refractive index, which essentially means that when you look at a prism or something like that, light tends to bend a certain way. And he proposed that you could get light to bend the other way if you so wanted. And this is the basis behind a perfect lens. Current limitations with optical microscopy are mainly due to something called the diffraction limit, which was divided by a guy called Ernst Abbe in 1873. Now the problem with that is that light is a wave, and as a wave it diffracts in certain ways. And the diffraction limit means that you can only resolve down to a very small spot, but a fixed size of spot. So you can get to about 200 nanometers across, and that's about, well, we're talking millionths of a millimeter here. And you can't go any further than that due to the wave-like nature of light. So that's a big problem.
The refractive index of a material is how much light slows down when it travels through such a material. So the light is traveling from air and into water. And when it hits the surface, it reflects a little bit, but it also transmits, and it bends at an angle that's related to the difference in refractive index between the two materials. Now water and pretty much all materials in nature have what's called a positive refractive index. So what's happening here is the light is going from air into water, and you can see that the light is bending towards the normal when it enters the more dense material, which is the T. If this wasn't T, but a negative refractive index material, something different would happen. The light wouldn't be on the left-hand side of the normal, it would instead be on the right. So light would come in this way, but then bend back on the opposite side to the surface normal.
The actual idea for a perfect lens, for it to be used to image things, came up with a guy called Sir John Pendry in about late 1990s, and it was demonstrated in early 2000s. And this idea basically uses a metamaterial, so a material that's comprised of very small structures, much smaller than a wavelength of light. And by arranging those structures in certain ways, you can amplify light waves and get them to diffract the wrong way. And you can see images you wouldn't normally be able to see on a much smaller scale.
With nanotechnology, you're dealing with things that you can't see. So it's really important that you have these tools that allow you to see a nanoparticle inside a cell that's really complex. So if you're doing bulk measurements, just on a lab bench, it's difficult to interpret the results, and that's where microscopy and good optical or high resolution optical microscopy and electron microscopy are so important, and more so now that we're dealing more with nanotechnology.
So we look at the interface between nanotechnology and immune cells using nanomaterials to try and control the responses where the body decides, the immune system decides whether it's going to attack an infection or a cancer or whether it's not going to. And the reason that's a nanotechnology or a nanoscale problem is because what these high-resolution microscopies are beginning to reveal is that there are a lot of exceedingly small structures, so down to the level of tens of nanometers or less. And these structures are critical to the way cells talk to each other. So when your immune system decides whether it's going to attack something, there are spatial structures at that size which are helping to mediate that decision. So the combination of, the ability to
If you look at nature, there are some stunning colour effects. Rainbows are amazing things. Stunningly bright, vivid butterflies from South America. Dragonflies, how do they achieve those gorgeous greens? We just need to know. If you take a butterfly and you look at its wing scales, it's got very tiny wing scales, about 50 microns by 100. We found that within the wing scale, which is more or less fingernail material, the butterfly had created tiny sculpted structures, nanostructures, which gave interference, which gave diffraction. Those effects combined can give you a variety of different vivid colour effects. From the electron microscope images, we discovered an intricate structure in the wing scale of the morpho butterfly. And what we decided to do was to replicate that on a much larger scale. Here we have a structure corresponding to the scale of the wavelength of microwaves with detailed ridges and with these Christmas tree structures internally. Then when we shine microwaves at this, it responds like light does to the butterfly wing scale. By unraveling the butterflies, we discovered a whole raft of new metamaterial type structures. If you structure matter on a fine enough scale, it doesn't respond in the simple way like a bucket of water or a piece of aluminium. It has new properties, new optical properties, new properties for different wavelengths. There was a fascinating paper